The next talk will be presented by Professor Eduardo Fontana. Eduardo Fontana is professor in the Electronics and System Department at UFPE. Eduardo is engaged in research and teaching activities in the fields of electromagnetic theory and applications, bioelectromagnetism, optical instrumentation, optical fiber sensors and devices applied to surface science resonance. So his talk will be Magnons in magnetic semiconductors. Eduardo, please, you may upload your presentation.
Thank you. Can you hear me?
Yes.
Just a second. Can you see my screen?
Yes, yes, great.
Okay. Well, I have been away from this field of knowledge for almost 40 years now. So I'm happy to know how the things evolved since then. So I'm going to just talk about some qualitative aspects of my work and my interaction with Sérgio from almost 4 years ago. That's the broad title, Magnons in magnetic semiconductors. But specifically, I'm going to talk about some landmarks of the master work I did on investigating the Magnons in selenide, chromium and cadmium selenide, which is a magnetic semiconductor. That's the summary of the talk. Just gonna make a only brief comment on my first interaction with Professor Rezende, and then I'm going to go on to show some aspects of the work that I carried out, and at the end some concluding remarks. In early '80, I was graduating, and then in the last semester, there was a position in the microwave laboratory. And this microwave laboratory was in the electrical engineering department at Federal University of Pernambuco, in our university. And Sérgio had an interaction with the department. He built this very nice laboratory. There was a position for one IC internship. And I just, I was interested in doing some scientific initiation. In fact, I was only doing, teaching assistant prior to that. And the last semester, prior to my graduation, I wanted to start some scientific, learning. And then there was this position in the lab. And it was just new by chance. Only one position, and I was immediately accepted because there was nobody else. So the work was comprised to, Sérgio was in the magnetism area, but because he was involved in the electrical engineering, he wanted to make applications of magnetic materials, and the one application was to build. He was doing some work with my colleague before, who was developing a EEG oscillator. And for my, internship, he proposed me to try to build resonance isolator for the X band. The effect is based on the resonance effect, which is non-reciprocal. If you have a moving wave on one direction, it interacts with the processing magnetization. If you have a wave going to the opposite direction, that if you have a circular polarization not aligned with the precession, it does interact. So because of that, you have high absorption in one direction, you have negligible absorption on the other one. And the task I have this relation between frequency and applied field, because the zero magnetic factor is about 2.8 gigahertz typically per Hertz. Then you have strong interaction in the microwave, as you guys all know, for a typical lab field of 3 kilohertz. Then the idea was to build this device. I mean, these devices are found, in those companies that make microwave devices. They build this, but our test was to position the ferrite slab, in the correct position where the effect has the maximum contrast. And we had, it was very difficult to position this. It was very artisanal. We did this and measure the response until we find the optimum position. Somehow we had to fix this magnet with the proper field that saturated the ferrites then we were able to do it. Okay, so that was my work, my internship. It was very interesting work. I liked a lot of electromagnetics, and I could see in action in this work. Well, after that, in my master, Sérgio proposed to investigate Magnons in cadmium and chromium selenide. I think that's the name in English. I'm not sure. Which is a magnetic semiconductor. And the idea was that it could enable magnetic control of electronic transport for novel device. And the research on this composites and these materials started in the early 60s. This material has typically a key heat temperature of 129.5 Kelvin. So below that, they have magnetic properties. And conductivity is typically on that range. It's a good resistor, but it can be changed through doping or crystal growth. And the objective of this work was to characterize the dispersion and elucidate Magnon relaxation mechanisms for low and high wave vectors, and as a function of temperature. The samples were grown by Dr. Gibart in France, and Professor Marcílio from the physics department, who also worked with Sérgio, was the person who prepared those very precise spheres with a very small diameter, 0.5 millimeters. And I just wanted to show you, it was very interesting for me to revisit my master's dissertation. I just found it. It was in my parents' parents' house. I thought I had lost it, but it was there, preserved. And I struck some diagrams that explain the scope of the work, the results that we obtained. Magnetic excitation is done by parallel pumping, which is the RF field is applied on the same direction of the static field, and if you start to increase the RF field, you start distorting the angular momentum, and then this distortion yields after a certain threshold two counter propagating magnons, and typically the wave vector that you produce is a function of the applied field, and the frequency of the magnet is half of the pumping frequency, and also the line width is proportional, to the threshold field, to threshold RF field. So if you measure the threshold, you are measuring the line width. If you measure given the frequency, the frequency of the magnet, okay, it's always fixed, and you change the wave vector by changing the static field. So you can you can, by doing that, get the dispersion relation and the dependence of the damping with the vector. I mean, all I'm saying, I'm sure everyone knows, okay? But I mean, since I've been away from this for almost 40 years, I was revisiting those concepts. It was very interesting to know. This is a setup that we employed to observe the parametric excitation of Magnons. We need high power, so we have a klystron, okay? And the klystron was modulated. There's a modulator there. Well, this modulator produces pulses that are 5 microseconds in this case wide, and because we don't want to hit the sample, and then we go through a traveling wave tube that produces an output of 3 watts continuous wave. I mean, if it was a continuous wave, I can control the power by, this attenuator that we have. Then we combine, we send the part to a cavity between a magnet, then with the circulated part comes back, then we balance the input with the reflected signal from the cavity. Then any imbalance due to some change in the cavity Q is going to be detected as changing signal here. And that's essentially the setup that we use. This is the original drawing of my master's dissertation. I mean, in those times, the drawings were made by hand by a drawer from the physics department. I think it was Carlos, his name. In fact, I met him. You can hear me? Oh, okay. I had some. Okay. So, can you hear me? Yes.
Yes.
Okay.
It's okay now.
I think it's my. Oh, I think it's here. Okay. And as I was saying, I met Carlos. His name was Carlos. Does anybody know that? I'm not sure. But I mean, I met the drawer in Recife Antigo about 3-4 years ago, I think. So this is because the effect could only be observed at low temperatures, and we want to make measurements on varying the temperature, going down to liquid helium temperature. We have this super varitemp with helium, liquid helium. You have some sleeves of vacuum and nitrogen, and you could control the flow of gas, cold gas through the sample, and by proper, control on the heat. Oh, sorry about that. Let me just go back here. Where was I? Okay. Yeah. So this is another aspect. I was talking about the temperature, but I'm going to talk here. So this is just a control of the iris to change the coupling of the input rate guide. There was a string, okay, which could be actuated externally. And we had this heater at the end of the system down the cavity. And by heating we could control the temperature, have a temperature sensor here. This is the control of the sample, because we also measured the dependence of the effects on the orientation, the crystallographic orientation. And so this is the sample is on sapphire tip. This is going vertically from the plane. And I am very proud to have used this mechanism here to rotate the sample, because this was extracted from my guitar. And, so it could rotate this worm gear here, which came from the guitar, an old guitar that was not used anymore. So, and we could control the rotation by doing that. So what else we have here? We have this is the shape of the pulse, 5 microseconds wide, repetition of 500 hertz, and we observed the onset of Magnons by a distortion on this shape. Okay? So by measuring the initial distortion, could have the measurement of the threshold field, which would yield the line width of the Magnons excited, as I mentioned there. And this is, as you people know, you are very familiar with that, this is a butterfly curve. This was measured for chromium and cadmium selenide at 4.2 Kelvin. Okay, this is a limiting field, HC. The left branch used in fact, use the branch that is for a magnon that propagates on 90 degrees with the static field. And the right branch uses that one that propagates at 0 degrees, and K equals 0. So measuring these numbers here, we have information on the line width, and measuring the H field, have a function of H field is a wave number, which is a function of H minus HC. And that's the way we measure the parameters. So these are several curves that we measure for the line width as a function of the wave vector. For different temperatures, we went up to 37.5. Beyond that, we could not observe anything significant. So, and also, we have those curves, and this was explained. I mean, this was analyzed. I mean, this was collaborative work with Sérgio and Mauricio Domingues, and their analysis mostly. The objective was also to elucidate what was the mechanism that determined, that depends on line width and wave vector for a high and low K. By analysis on rate equations and identifying the coefficients of the rate equations, they show that the linear region was due to 3 Magnon relaxation, and the low K region was to decay into degenerate modes and subsequent 3 Magnon relaxation. So this was the contribution of this work. And this went on to be published on the Journal of Applied Physics in 1984. This was a discussion of the paper. I just want to observe how this master's dissertation I did. I mean, this was concluded in 1983. And I had to hurry, and I'm not sure, but I think my dissertation is the only, I think at the time we have typewritten texts, but all equations in my dissertation were made by hand. Okay? But they look pretty nice, I think. Okay, so, but I had to do it by hand because there was no time to do it in typewriting. I think, I'm not sure if that was the reason, if that was the way to do equations 40 years ago. I'm not sure. I think we did equations by typewriters. So. I just want to mention that, my training started with Professor Sérgio, and I learned from him lots of basic concepts. One important concept was how to observe physical phenomena and try to exploit that for doing some engineering device, some instrumentation. And that's I always practiced in my career. Okay? A basic thing that I learned from the work with Sérgio Rezende was always to observe if something, to observe the physical phenomenon and try to use that phenomenon to make a device. So, the same methods that were used to analyze, to analyze rate of population change of magnons or bosons or whatever, using rate equations, I still use. I mean, I don't work with magnetism at the moment, but I work with several phenomena in which I make devices, spectroscopy, reflectometry. We deal with the resonance concepts in engineering a lot, and we do that a lot. Just to show you that, I mean, I recently published a paper, which is an application in engineering, which is based, I mean, the model is based on rate equations. The same rate equations used to determine the relaxation mechanism, the relaxation mechanism in the Magnon process, in the mass dissertation that I developed. So this partition, this modeling here using several couple rate equations to determine the rate of transport of molecular species in the oil through a gas phase. So this is applied to measure dissolved gases in transformers, in high voltage transformers. By measuring those gases, you determine the possibility of malfunction of the equipment. So we developed the sensor, but also the modeling based on rate equations. Just published that paper recently, just to show that everything is all linked. Okay, all the basic equations are almost the same. Differential equations are similar in different parts of knowledge. So that's what I wanted to say. And I would like to conclude by saying that, sorry about that. Happy birthday to Sérgio, and like to thank him for letting me be part of his journey. I mean, he's an example of integrity, ethics, and leadership, and is very inspiring for all of us. Thank you.
Thank you, Eduardo. Let's hear Eduardo again.
Remove here the.
Okay. Thank you, Eduardo. Let's move on to the next talk.